stretching 3.4 kilometers across the St. Lawrence River. This is Canada's newest and toughest crossing, the Samuel de Champlain Bridge. With 3 months to go before it opens, engineers are locked in a race against time.
The clock is ticking. We're now in the final push.
What technologies make it strong enough to handle 60 million vehicles a year? And how does its design beat extreme winter weather?
This bridge has to be built tough in order to survive.
We unlock the engineering secrets that make this one of the most advanced bridges in North America. From its aerodynamic profile that stands up to the strongest winds, to a skeleton forged from super strong corrosion-resistant materials, to reveal what it takes to build the ultimate super bridge. Montreal, Canada. The nation's second-largest city is a major hub for business and commerce. Montreal's success depends on its big bridges spanning the St. Lawrence River. They must move people and goods between the city, the rest of Canada, and the US. But building and maintaining big infrastructure in this part of North America is a huge engineering challenge. Over 12 months, Montreal's climate fluctuates wildly. In summer, temperatures can soar to a scorching 35 degrees centigrade. In winter, the mercury can plummet to -30. Fast-moving ice flows pack the St. Lawrence River, and freezing winds batter the city. To keep the city connected and moving in all weathers, engineers in Montreal are building this. The Samuel de Champlain Bridge. It spans 3.4 kilometers and costs over 4 billion Canadian dollars. The bridge is built using innovative technology, baked into its mighty structure to stand up to everything Mother Nature throws at it. Ingenious cables stop monster chunks of ice crashing onto cars and pedestrians. A deck structure that stays rock solid in the strongest winds. Expanding joints stop the bridge cracking up as the temperature changes. An ingenious drainage system flushes away corrosive salty water before it destroys concrete and steel. All these elements combine to make the new Samuel de Champlain the ultimate bridge. Construction work starts on the bridge in 2015. Engineers sink 37 sets of pillars, called piers, into the land and the St. Lawrence riverbed. Then they lay a steel platform on top of the piers. Next, they use giant floating cranes to place 9,600 concrete deck slabs. Today, this elite team work around the clock to complete construction and prepare the bridge for its opening in just 3 months' time. Once finished, this critical artery must carry 60 million vehicles and $20 billion worth of cargo each year. Stay open 24/7 in all weathers and survive for at least 125 years. The lifespan the Canadian government specifies for new critical bridges. Chief Engineer Guy Maillard leads a team in charge of the Herculean task of building this super bridge.
There's daily stresses on us, the entire team, to do whatever we can to get the bridge open in time. Because this bridge had to last for 125 years, it had to be built tough and resilient.
The stakes couldn't be higher for Guy and his team. Next door to the construction site is a big reminder of what will happen if they fail. In 1962, Montreal opened the first Champlain Bridge over the St. Lawrence River. It was expected to last for a century. But within 30 years, the bridge started to crumble. Now, after 5 decades in service, it needs round-the-clock monitoring and costly maintenance. Alex Chemenier is part of the team tasked with keeping the old bridge operational until the new one is complete.
To give an idea of how much these repairs have cost over the past few years, since 2014, approximately $300 million has been invested into the bridge. So we're looking at approximately $50 million to $60 million a year being put into the bridge just to ensure that it stays strong and it stays standing until the new bridge opens.
Along the length of the bridge, broken concrete exposes rusted rebar beneath. Engineers call this damage spalling.
Here we have some typical damages that we see across the bridge. We have some spalling, we have some exposed rebar. Typically, when the damages get a lot worse than this, we'll then intervene and do some patches to the concrete.
The cause of the spalling is the crucial chemical Montreal uses to keep the city's roads ice-free. Ever since the 1960s, the city covers its roads and bridges with salt. 130,000 tons of it every year. Salt is an effective way to melt ice, but it destroys concrete structures. When de-icing salts melt away snow, they dissolve into the liquid water and can trickle down the side of the bridge. Over time, this salty water seeps through the concrete and contacts the steel rebar inside. The salt water contains chloride ions. These react with the steel, causing it to rust and expand. Eventually, the bridge is so cracked and damaged that large chunks begin to break away. Left unchecked, the bridge's steel skeleton will become so corroded that the entire structure could collapse. The challenge for Guy and his team is to make the new Samuel de Champlain Bridge 100% salt-proof. To solve the problem, they must completely rethink the very fabric of this bridge.
In planning the new bridge, we really learned from the old bridge, and we were quite prescriptive in the type of materials to ensure that the bridge would perform well over its intended 125-year design life.
They choose to build the skeleton of the bridge from stainless steel rebar. This chromium-enhanced metal is 10 times more resistant to corrosion than traditional steel. Marcel Martineau's team then encases this skeleton in the ultimate protective concrete layer.
We have to ensure over 125 years that no corrosion will start on the rebar. That's the main challenge. The type of mix we're using for the deck, it's impervious concrete to ensure that the chloride ion won't go to the rebar and that start corrosion.
Engineers combine stainless steel rebar and corrosion-resistant concrete to produce the bridge's 9,600 deck slabs. Installing them onto the bridge structure takes 22 weeks. Today, Marcel's expert team races to fill the stitches between the slabs with more concrete. Its mix contains less water. This makes it denser than traditional concrete. Workers use special machines to eliminate air pockets to guarantee the concrete's salt-proof qualities.
placing and the finishing of the concrete is as important as the mix itself. If it's not done properly, at the end, the result, we won't achieve the 125 years life expectancy.
This section of roadway is just one small part of an ingenious drainage system. The bridge's designers engineer the structure like a giant sink to reduce the concrete's exposure to corrosive salt. The shape and angle of the deck's camber directs water towards drains sited along the edge of the roadway. Water flows into an intricate system of pipes up to 60 centimeters wide that run through the structure and down its pier legs. The pipes release the salty water a meter above the waterline. This reduces the amount of concrete exposed to the corrosive solution. Workers spray every square centimeter of set concrete with a synthetic resin to protect the bridge even more. This waterproof membrane is part of a layered system designed specifically to prevent the damage salt causes.
To ensure that we won't have corrosion on this bridge, we start with a good drainage system. We then have a thick layer of asphalt. We then have a waterproofing membrane. We then have high-performance concrete, which is much more resistant to salt penetration. And then we have the stainless steel rebar. And the old bridge had none of these. So I can say in conclusion, there's no way that salt is going to corrode the steel on this bridge.
The super bridge is now immune to the damaging effects of road salt. But this megastructure must withstand more climatic extremes to last 125 years. What technology protects it from Montreal's huge seasonal temperature fluctuations? And what is this bridge's secret for beating destructive winds? In Montreal, the new Samuel de Champlain Bridge opens in 3 months' time. It must be robust enough to serve the city every day for a minimum of 125 years. If engineers get its construction wrong, this new bridge could suffer the same fate as its crumbling older neighbor. One of the biggest challenges facing the new bridge's engineers is building a structure that copes with Montreal's huge temperature range. In summer here, the mercury can top 35 degrees centigrade. In winter, the temperature can plummet to -30.
It's important to keep in mind what 125 years means. In fact, the structure will be solicited by thermal variations in temperature, and these will be repeated every day for the next 125 years. So you really have to look at each individual component, understand how it's going to behave under that extended design life, and then design it accordingly.
Montreal's weather cycle will have a big impact on the city's new bridge. Almost all the bridge's components expand when they heat up and shrink when they cool. Individually, these variations in size are tiny, but combined along a 3.4-kilometer-long bridge, the difference can be huge. As Montreal freezes in the winter and warms in the summer, the bridge can change length by up to 3 meters over the year. If engineers ignore these fluctuations, the bridge's deck could buckle as it expands or crack as it contracts. To solve the problem, designers build 8 gaps into each of the bridge's 2 road decks. Each gap is up to 1.6 meters wide. These create space for the bridge to expand into. The gaps stop the structure from cracking up, but make it impossible for vehicles to pass. The solution is these ingenious expansion joints. They're designed to both fill the gaps and let the bridge flex. Intensive factory tests ensure each joint can withstand extreme temperature changes throughout the year. Today, project manager Alexis Lauzon oversees the final joint installation.
An expansion joint is an important part of a bridge to make sure that the bridge can move freely throughout the seasons. This expansion joint will take a lot of abuse throughout the years.
Alexis' crew installs 8 expansion joints into both of the bridge's road decks. The sides of each joint attach to the ends of 2 road sections. As the bridge expands or contracts, the joint strips, up to 20 meters wide, move along rails. They react to the bridge's lateral and vertical movements. Buffers ensure the joint's metal strips remain evenly spaced as they move. And spring bearings beneath the strips distribute the load of vehicles through the bridge's concrete structure. Alexis' team swings into action. With 3 months to go before the bridge opens, they're under intense pressure.
The expansion joint that we're going to see today is quite heavy and quite big. We have a 16-meter piece that weighs around 16 tons. The workers need to be really meticulous because any wrong movement could be fatal. Actually, it could damage the bridge. It could also damage the expansion joints, and there's a lot of workers around the lifting process.
A mighty crane lowers the huge 16-ton joint into position. The team removes some steel obstructing the gap. Then the joint slots in perfectly. Expansion joints stop the bridge's decks from breaking up as temperature variations make them stretch and shrink. But the bridge's changing shape presents additional engineering challenges for this team. 6 of the huge deck sections attached to pier legs sunk deep into the St. Lawrence riverbed. These sections could break the joints to their legs as they expand and contract. And there's another problem. Montreal sits in an active seismic zone. Over the next 125 years, the city will experience at least one major ground movement. When it happens, there's a real risk the bridge will sustain catastrophic damage.
If the structure were not flexible under a seismic event, it would transfer tremendous forces because the structure would be much more rigid, which could potentially severely damage the piers.
Engineers install bearings that allow the deck to slip across its legs and stop the bridge from breaking apart.
The bridge rests on these bearings. These bearings allow the bridge to move. And I've just made a measurement. I can see that the structure has moved when we go from hot temperature to cold temperature, about 7 centimeters since it was set in place by the marks that are left on the stainless steel plate.
Free to move and flex, the new Samuel de Champlain Bridge is ready to beat extreme temperature fluctuations and any future earthquakes. The engineers' next challenge is to make sure that this mega bridge can combat devastating winds and stand firm when hit by an onslaught of river ice. In Montreal, the new Samuel de Champlain Bridge must open in 3 months' time, ready to serve the city for at least 125 years. The bridge has 6 lanes to carry more than 1 million vehicles every week. But this mega crossing accommodates more than just cars and trucks. On one side is a pedestrian walkway and cycle path. A rail line will run down the center, directly into Montreal's central station. The bridge must be a massive 60 meters wide to accommodate all these elements. But in Montreal, size makes you a big target for a powerful force of nature. Winds in the St. Lawrence River Valley can reach speeds in excess of 100 kilometers per hour. To make the bridge super tough, engineers space its pier legs just 84 meters apart. This short length reduces the distance each deck section must span and bolsters the bridge against fast-moving air pushing on its massive structure. But one crucial part of the bridge needs a different method of support. Bridge piers cannot obstruct the 145-meter wide shipping canal running parallel to the river. To span it, engineers must suspend a critical 240-meter long section of the bridge. 30 cables attached to the 170-meter tall tower take the load. This leaves the shipping canal beneath the bridge unobstructed by piers. But suspending sections of bridge deck from cables makes them vulnerable to strong winds. The structure of some bridges forces air faster over the top of their decks than underneath it. This creates an area of high pressure beneath the bridge. Just like an aircraft wing, the deck can lift up, stressing the bridge's joints and damaging its deck. Every time the wind blows, there's a risk the new Champlain Bridge will suffer damage.
The bridge in the Montreal environment has to be aerodynamically stable in order to ensure that the bridge will not oscillate unexpectedly under intense winds.
Engineers deploy an innovative solution to eliminate the danger. They design gaps between the bridge's road decks and rail line. These gaps vent and disrupt the fast-moving air, preventing high pressure from lifting the bridge and damaging its deck. On paper, the bridge looks ready to withstand the dangers created by strong winds. But wind presents another engineering challenge for a cable-stay bridge.
By their very nature, cable-stayed bridges or suspension bridges tend to be very flexible, and so the interaction with the wind becomes very important.
As history proves, build a bridge that's too flexible, and wind will tear it apart. November 1940. Tacoma Narrows Bridge, Washington State. 4 months after opening, 65 km/h winds cause the bridge to twist and sway. The movements become so violent, the bridge breaks apart and collapses. The cause is a then little understood phenomena called aeroelastic flutter. Suspension bridges twist fast-moving air into mini whirlwinds that pull at the bridge deck. The shape and weight of most bridges means these vortices cause only a slight movement. But the Tacoma Narrows Bridge contains a critical flaw. Due to its narrow, lightweight deck, the vortices cause greater movement. Sustained winds make the bridge wobble and oscillate. The twisting eventually becomes so violent that the bridge collapses. To make sure the new Champlain Bridge doesn't suffer the same fate, engineers must test its design under every wind condition before construction.
You cannot really predict how well the bridge will be performing until you undergo some very intensive wind modeling to make sure that the bridge will respond correctly under wind loading.
Engineers enlist the help of aerodynamics expert Dr. Peter King. His team at Western University, Ontario, build a scaled-down bridge model costing 70,000 Canadian dollars. They test it in a wind tunnel to predict how the full-scale new Champlain bridge will behave.
The model is a complete dynamic replica of the bridge, so it has the right mass properties, the right stiffness properties, and replicates all of the dynamic motions of the bridge. The model is at a geometric scale of 1 to 150, which has a velocity scaling of about 12 to 1. So that means everything that you see in the wind tunnel is happening about 12 times faster than it would in real life.
The model withstands simulated wind speeds of up to 180 kilometers per hour coming from different directions. That's 3 times faster than the wind that destroyed the Tacoma Narrows Bridge. To improve the new bridge's aerodynamics even more, engineers modify the sides of its backspan. This is the part of the suspended bridge that counterbalances the section crossing the shipping canal parallel to the river. They hope this adjustment will stop the bridge from shaking itself apart.
Here in the main span, we have a solid pedestrian barrier on the leading and trailing edges, whereas in the backspan, it's completely open and allows the wind to go straight through.
This tiny modification does the trick. The different barriers disrupt the wind flow over the bridge and reduce the pull on the deck. There's no danger the full-scale bridge will twist itself to destruction. The bridge can beat wind. But there's still more Mother Nature can throw its way. How will the bridge defend itself from concrete smashing ice flows? And what smart technology stops big chunks of ice falling from the bridge and crushing cars below? In Montreal, the new Samuel de Champlain Bridge opens in just a few months' time. It must be ready to serve the city every day for 125 years. The minimum lifespan the Canadian government specifies for new, critical infrastructure. Workers battle freezing temperatures to get the bridge finished on time.
When our goal to open the bridge in June, the clock is ticking. We're now in the final push.
This super bridge must survive over a century of brutal Canadian winters and the yearly onslaught of powerful ice flows.
Montreal is subject to winter freezing, where the temperature can go down to -40. This will mean that the river will freeze over. It can freeze up to 0.9 meters thick. This ice breaks up. It will generate large flows of ice that will impact the piers.
Blocks of ice can inflict critical damage to big structures that stand in their way. The current in the St. Lawrence River accelerates ice up to speeds of 4 kilometers per hour. A flow traveling this fast, measuring 45 meters across and 1 meter deep, grinds at the pier legs with the same force as the weight of 10 trucks. Cracking and eroding the concrete. This footage from the 1960s shows that ice flows on the St. Lawrence River have always been a problem. Just 2 years after the opening of the old Champlain Bridge in 1962, Montreal builds another huge span across the St. Lawrence. This massive structure is not a traffic crossing. It's the first line of defense to protect Montreal's bridges and shoreline. It's an ice-breaking megastructure.
In the winter, you'll have large ice flows which will build upstream, and then as they flow downstream towards Champlain Bridge, they will impact the icebreaker structure, and the columns of the structure will cleave these ice flows into smaller pieces of ice, and these are less damaging.
Even with a dedicated icebreaker, the old Champlain Bridge, 300 meters downstream, is covered in scars sustained in battles with the ice. Alex's vigilant team must react fast to keep the crumbling structure standing.
On our piers, we actually have steel lining just at the water level to ensure that when ice does hit the piers, that the concrete itself is protected. But over time, sometimes the steel lining disintegrates with the water and concrete can be affected. We do rapidly intervene to reinstall that steel liner in order to ensure that the structure remains intact.
This old icebreaker has only a limited lifespan. City engineers plan to decommission the structure in the future. For most of its life, the new bridge must face the ice onslaught alone. For the bridge to survive, it needs the strongest concrete legs of any structure across the St. Lawrence. Concrete is a mix of water, sand, gravel, and cement. Increasing the ratio of cement to water raises the concrete's density and makes it super tough. Engineers then add a secret ingredient that changes the concrete's chemistry to make it even stronger. At the atomic level, when cement mixes with water, the reaction creates calcium silica hydrate, which bonds the concrete mix together. But the same reaction also produces other particles that disrupt the bonds, forming weak points in the concrete. When engineers add a chemical called silica fume, it reacts with the disruptive particles, turning them into more calcium silica hydrate, making the overall structure stronger than ordinary concrete. In 2015, construction work on the bridge's piers begins. Engineers pour the pier bases on land and let them set solid. Then they use a floating foundation installer to sink 38 bases into the riverbed of the mighty St. Lawrence.
The mix used for the pier leg is the strongest mix I use in my 30 years career. And I learned a lot on concrete, especially for very, very strong concrete.
Engineers add an extra 30 centimeter thick concrete layer at the pier's bases for additional protection. Today, Marcel checks if the team's hard work has been worth it.
These piers were installed at the end of December 2016. That means so far we had 3 winters. So far the behavior is perfect. We're really confident that it will last 125 years for ice abrasion.
Samuel de Champlain Bridge's super strong concrete makes it tough enough to resist destructive ice flows. But new challenges lay ahead. How does this super bridge prevent falling ice that endangers lives? And what technology turns it into an intelligent machine that keeps check on its own health? Workers in Montreal race to complete the city's new super bridge. 37 sets of giant concrete pier legs, 84 meters apart, support most of the bridge's 3.4-kilometer span. A total of 60 cables attached to either side of a 170-meter tall tower hold up a 500-meter section. Only when all the cables have been installed will the bridge be ready to open.
Completing the cables is significant because the bridge at that point will be structurally completed, and the only things that will remain are finishing works.
The pressure is on Jonathan Smard to finish the job.
There's 4 holes, so this is the 4 last cable. After that, the job's gonna be done. Everybody's looking at us and they want their bridge. They want us to finish this bridge. For Montreal, we need this bridge.
Jonathan and his team must install special sleeves that encase the full length of the bridge's 60 cables.
The first step is lifting the sleeve with the tower crane, and we attach this to the anchor up there. When the sleeve is in position, we install cable.
Cable sleeves protect the metal inside from ice and rain. But come winter, some sleeves can create dangers to both traffic and pedestrians. 2014, Charleston, South Carolina. The Ravenel Bridge closes when large chunks of ice fall on passing cars, shattering their windscreens. 9 vehicles sustain damage. It's the way water freezes on the bridge's cable sleeves that's a big factor in creating the falling ice. Temperatures fluctuating just above and just below freezing causes the problem. Rain coats the sleeves in water. When the temperature drops below 0, the water freezes. Temperatures then rise, but not by enough for the ice to melt. New rainwater falls on top of the ice and freezes when the temperature drops below 0 again. Soon a thick layer of ice completely encases the sleeve. The ice becomes heavier until it breaks away, crashing onto the bridge deck below. The designers of the new Champlain Bridge must stop its cable sleeves shedding dangerous, large chunks of ice. The ingenious fix is a unique design running the length of the sleeve. A series of equally spaced hoops.
You can see that there are circular ribs. This is a bit different from what we would see on most bridges. The idea here is with these circular ribs will help shed water more efficiently.
The ribs are spaced at 30-centimeter intervals. Because of the cable's slanted angle, when it rains, water accumulates behind the ridges, and most of it runs off and falls onto the bridge deck as harmless drips. The water freezes in chunks trapped between the ribs. The ice sheds in smaller pieces, so when it falls onto the bridge deck, it's not dangerous to passing cars and pedestrians. The sleeves are now in place. Next, Jonathan's team must thread the cable strands.
Outside it's looked like one big cable, but inside there's 127 small cable. You can see here we have a pre-cut cable. That's the cable gonna be in this sleeve.
Splitting the cable into so many strands cuts maintenance time and cost. Future maintenance crews will only have to replace damaged individual strands. They will not have to switch out an entire, super heavy cable. Engineers use winches to thread each strand, one by one, up the sleeve and through to cable anchors in the tower. They then pull the ends downwards and secure them to the deck.
These are 5 times the strength of normal steel. These strands themselves are actually doing all the work in terms of supporting the weight of the deck structure.
The next challenge is to tighten the cables to hold the estimated 12,800-ton weight of the bridge's span. What ingenious tool makes sure every cable is stretched to the correct tension? And what technology makes this bridge intelligent enough to know when it needs maintenance? In Montreal, workers race to ready the new Samuel de Champlain Bridge for its grand opening. Once complete, the bridge must support over 1 million vehicle journeys every week and serve the city for 125 years. Advanced super-strong materials and an ingenious design make the bridge windproof, ice-proof, and flexible enough to cope with Montreal's massive temperature variations. But its lifespan depends on identifying and repairing problems before they become critical. Limited access to inspect the structure's interior is a big reason why the old Champlain Bridge is failing. Engineers cannot see critical issues until they show up on the bridge's exterior. By then, it's too late to solve the problem at source. All they can do is patch up the damage. So engineers are building the new bridge to have all area access to avoid these past mistakes. Hatches, walkways, and crawl spaces allow them to inspect every square centimeter of the bridge's 3.4-kilometer span. But they still need help to identify potential problems as early as possible. Borja Baez leads a team tasked with making the bridge intelligent.
We've covered this new Champlain Bridge from head to toe with sensors like GPS, corrosion, displacement. This bridge is going to be like one of the smartest structures in the world.
Borja's team installed 226 sensors that send data 24/7 to a central monitoring station.
This is a strain gauge installed in a piece of steel, and just a very small deformation of less than a millimeter, there would be an alert, and the maintenance team would check what's happening in the structure.
The cloak of sensors makes the new bridge hyper-vigilant. Alerting humans to problems early on is a big step towards the bridge achieving its mission of serving Montreal for 125 years. At deck level, engineers race to thread and tension the last remaining cables. They must tighten each of the cable's 127 strands. Mechanics deploy a special tool to tension them one by one.
The gentlemen here are key in stressing the cables to the correct stress level. They put a hydraulic jack which will pull the strand, and then they'll stick these wedges that will lock the strand into place.
Over the next 20 days, the team pulls out all the stops to finish the job. The last cable plugs in right on schedule.
After 1 year and a half, we finally finish the last sleeve. It's an important step of the new Champlain Bridge. The iron workers are very, very proud of this big project. They put a flag, they took photo, they are so proud, and they work so strong to finish this big project. It's a big step for us.
Two months later, at 5 a.m. on the 24th of June, the Samuel de Champlain Bridge opens. The first vehicles roll westwards over the St. Lawrence, on Montreal's newest and toughest crossing. Over 4 years, a 1,600-strong workforce poured 93,000 cubic meters of concrete, laid over 72,000 tons of steel, tightened 1.2 million bolts to span the mighty St. Lawrence River. Its mission accomplished for Guy and his team.
To work on a project of this magnitude is almost a dream, because you don't build these sort of bridges very often. And I think every single person that has worked on this bridge is proud of having contributed, because it is a landmark structure in Montreal, and it's going to be there for many generations to come.
The Samuel de Champlain Bridge is tougher and will carry more vehicles than any other bridge in Canada. Built into its mighty frame are 5 engineering marvels that make it the pinnacle of bridge design. Ribbed cable sleeves stop dangerous ice falling onto passing cars. A vented design keeps the deck steady in the strongest winds. Expanding joints allow the bridge to flex when the temperature changes. Pier legs built from super-strong concrete withstand the force of crushing ice. Innovative drainage gets rid of corrosive, salty slush. This is a bridge that is big, tough enough to survive anything Mother Nature throws its way, and is set to become a Montreal icon. The Samuel de Champlain Bridge is built to be the ultimate